Hey friends, and welcome back to my science studio. In this next series of videos, we're going to focus on different types of chemical reactions. But before we dive into combination, decomposition, or even combustion reactions, we need to first pause and make sure we understand something really important: the law of conservation of mass. And this law is the reason why we balance chemical equations. And trust me, whenever you have to predict the product of a chemical reaction on your homework assignment or on an exam, you will be expected to balance the equation afterward. So let's just jump right in. You see, the law of conservation of mass states that matter cannot be created or destroyed during a chemical reaction. It can only be rearranged. In other words, matter is conserved in the process. And if you remember, matter is anything that has mass and takes up space. And one way I like to explain this to my students is by using the analogy of baking a cake for your best friend's birthday party. Maybe the recipe calls for 3 eggs, 2 sticks of butter, 1 cup of flour, maybe 1 cup of sugar. When you bake the cake, do those ingredients just disappear? Of course not. They're simply transformed into something new: your cake. And you see, the same idea applies in chemistry. The same ingredients that go in are the same ingredients that come out. They've just been rearranged. And just like a recipe, scientists use chemical equations to show how this rearrangement happens. So let's go over some key terms. The substances you start with in a chemical reaction are called your reactants. These are your starting materials, and they are always written on the left side of the chemical equation. In our cake example, that's your ingredients: the eggs, butter, flour, and sugar. These are your reactants. The arrow in a chemical equation means yields or produces, and everything to the right side of this arrow is called the product, what is formed as a result of the reaction. In our example, the product would be your one cake. The plus sign does not mean adding like in math. Instead, it means reacts with or and. So we would read it as 3 eggs react with 2 sticks of butter, reacts with flour, and reacts with sugar to produce 1 cake. But now let's talk about the numbers you see in chemical equations. The large numbers written in front of a formula are called your coefficients, and these tell you how many molecules you have. For example, a 3 in front of the H2O means 3 water molecules. But the small numbers written after an element symbol are called your subscripts. These tell you how many atoms of that element are in one molecule. So for example, the 2 in H2O means there are 2 hydrogen atoms in one water molecule. And if there's no coefficient written, it's understood to be 1. And we never write the number 1 as a coefficient or a subscript for that matter. So in this example, we have 1 oxygen present in this 1 molecule of water. So what's the big takeaway from all this? You see, for an equation to be balanced, it must satisfy the law of conservation of mass. That means the number of each type of atom on the reactant side must equal the number of each type of atom on the product side. And we balance equations by adjusting the coefficients only, kind of like balancing a seesaw. Both sides need to be equal for the system to be balanced. Okay, so now the big question is, how do we actually balance a chemical equation? Well, let's walk through this first example together. Here we have a combination, also called a synthesis reaction, but more on reaction types in another video. And our equation reads, H2 reacts with O2 to produce H2O. And first things first, we got to identify the atoms present. On the reactant side, we have hydrogen and oxygen. On the product side, we also have hydrogen and oxygen, which is exactly what we want. You see, if an atom appeared on one side but not the other, that would totally violate the law of conservation of mass. Matter doesn't just disappear or appear. Okay, now it's time to count atoms. The subscript 2 next to hydrogen tells us we have 2 hydrogens. And on the left, we also have 2 oxygens. On the right, we have 2 hydrogens and 1 oxygen. And here's a tip I always give my students. Balance the element that appears in the fewest places first. In this case, oxygen is a great place to start because there's only one oxygen on the product side. So we added 2 in front of H2O. Now we have 2 oxygens on the right, which is good. But whenever you add a coefficient, you must ask yourself, did I change any other atoms? And you did, the hydrogen. You see, just like in math, that coefficient 2 distributes to the entire formula. So 2 times 2 hydrogens makes 4 hydrogens, and 2 times 1 oxygen makes 2 oxygens. So now that we have 4 hydrogens on the right, we have to fix that by balancing the reactant side. How do we do that? Well, you see, if we added 2 in front of the H2 on the left, 2 times 2 makes 4. So now let's double check what we have. On the left, we have 4 hydrogens, and on the right, we also have 4 hydrogens. On the left, we have 2 oxygens, and on the right, we also have 2 oxygens. Well, our equation is balanced. Now let's try another one, but this time I want you to pause the video and try it first. When you're ready, press play, and we'll go over it together. So in this equation, we have N2 reacts with H2 to produce NH3. Well, first identify your atoms. On the reactant side, we have 2 nitrogens and 2 hydrogens. And on the right, we have 1 nitrogen and 3 hydrogens. And the first thing that should catch your eye is the nitrogen. We have 2 nitrogens on the left, but only 1 on the right. So if we added 2 in front of the NH3, that balances out the nitrogen because now we have 2 on both sides. But it also changes the number of hydrogens, right? Because 2 distributes to the 3 hydrogens in the NH3, and that gives you 6. So now we have 6 hydrogens on the right. So to match that, we have to make the left side also have 6 hydrogens. And we have 2 so far. So if we add a coefficient 3 in the front of H2, 3 times 2 makes 6. So now let's double check. The nitrogen, we have 2 on both sides. The hydrogens, we have 6 on both sides. And now we're balanced. Now, if I can give you 3 common mistakes to avoid, it would be the following. The first is to never change your subscripts. Instead, you only adjust the coefficients. The second is to always recount your atoms after adding a coefficient. So don't forget to ask yourself, did I change another atom in the process? And the third, use the smallest whole number ratio. You see, if all the coefficients can be divided by the same number, you got to simplify them. In this example, we have a 1 to 3 to 2 ratio, which cannot be reduced further, so it's already simplified. Now let's try a slightly harder problem. Here we have C3H8 reacts with O2 to produce CO2 and H2O. And this is an example of a combustion reaction. And I promise we'll go deeper into combustions in another video, but for now, here's what I want you to know. In a combustion, the reaction always involves some type of hydrocarbon, so something made up of carbon and hydrogen, reacting with oxygen to produce carbon dioxide and water. And my number 1 tip for balancing combustions is this. First, balance your carbons, then your hydrogens, and leave oxygen for last. Why? Because oxygen usually appears in multiple places, and O2 is, well, by itself, which makes it easiest to fix at the end. So let's start counting. On the left, we have 3 carbons, 8 hydrogens, and 2 oxygens. On the right, we have 1 carbon, 2 hydrogens, and we actually have 3 oxygens present on the right side, 2 from the CO2 and 1 from the H2O. The first step is to balance your carbons. We have 3 carbons on the left, so if we add a 3 in front of the CO2, that'll balance out the carbons. Next, balance your hydrogens. We have 8 hydrogens on the left, so if we add a 4 in front of the H2O, 4 times 2 gives us 8 hydrogens. So we're balanced with the hydrogens. We've ignored oxygen until now, How many do we have on the left? Well, we have 2, and on the right, well, we got to do a little bit of math here. So we have 2 oxygens in CO2 times the 3 makes 6, and 1 from the H2O times 4 is 4. So 6 plus 4 oxygens gives you 10. So to get 10 oxygens on the left side, we have to add a 5 in front of the O2, because 5 times 2 is 10. And because the coefficients are already in the lowest whole number ratio, we're done. Now let's try a more challenging problem. The reaction reads, AlBr3 reacts with K2SO4 to yield KBr and Al2SO4 3. Now I really encourage you to pause this video, give it a try on your own, and then come back and check your work with me. The key idea with this problem is that if you see a polyatomic ion, keep it together. Do not try and break apart the atoms. If you recall from one of my previous lessons, polyatomic just means many atoms bonded together. And when they appear unchanged on both sides, treating them as a single unit saves you both time and stress. So let's first start by identifying what's present. On the reactant side, we have aluminum, Al, we have Br, bromine, we have K, which is potassium, and we also have sulfate, which is a polyatomic ion that has the form SO4 with a -2 charge. On the product side, we also have aluminum, bromine, potassium, and sulfates again. And remember our rule, if a polyatomic ion appears on both sides of the equation, keep it grouped together. So instead of splitting the sulfate into sulfur and oxygen, we treat SO4 as one unit. Now let's count. On the left, we have 1 aluminum, 3 bromines, 2 potassiums, and 1 sulfate. On the right, we have 2 aluminums, 1 bromine, 1 potassium, and 3 sulfates. Remember that subscript 3 tells me that I have 3 sulfates present. Treat it as a unit. The first thing that catches my attention is the aluminum. There are 2 aluminums on the right and only 1 on the left. So we added 2 in front of AlBr3. And that balances out the aluminum. But it also changes the bromine because now I have 6 bromines, right? 2 times 3 is 6. To balance the bromines, we have to add a 6 in front of KBr on the right. But that also changes the number of potassiums. Now we have 6 potassiums on the right. And since K2SO4 gives us 2 potassiums at a time, we have to add a 3 in front of K2SO4 on the left. And notice what just happened. Without even trying, the sulfates are now balanced. We have 3 sulfates on the left, 3 sulfates on the right, and doing a final check, we have 2 aluminums on the left, 2 aluminums on the right, 6 bromines on the left, 6 bromines on the right, 6 potassiums on the left, 6 potassiums on the right, 3 sulfates on the left, 3 sulfates on the right. And our coefficients are in the lowest whole number ratio. So we're done. And the final takeaway from this lesson is that balancing equations isn't just about memorizing these random steps. It's about recognizing patterns, keeping your polyatomic ions together, and, well, doing a little bit of trial and error until you get the hang of it. But why does this matter anyhow? You see, balanced equations show up everywhere, whether that's in medicine, industry, or in the environment. Pharmacists rely on balanced reactions to create safe medications. Engineers use them to design efficient chemical processes. Guys, even the air we breathe depends on balanced chemical reactions happening constantly. So this skill isn't just for your chemistry class, it's part of how the real world works. And that's all for today. In our next lesson, we'll start breaking down types of chemical reactions, beginning with synthesis and decomposition reactions. And if you'd like a video with only practice problems for balancing equations, please drop a comment below and I'll add it to my practice problems playlist. Thank you guys so much for watching. If you found this video helpful, please don't hesitate to like and subscribe. In the meantime, happy studying.